Hey guys, we're going to be bringing physics to life today, and I want to show you how one law governs everything from a light bulb to one of these, Geiger counter. So what does a light bulb and a Geiger counter have in common? Well, they say light is a photon, and they say that gamma is a photon, a gamma ray. Now, a gamma ray is released at the end of both alpha and beta decay modes as the daughter stabilizes. Okay? That's when the gamma is released. So what we have before you is the Bulletin of the Bureau of Standards Volume 3. And this is from 1907. So this predates much of the U.S. nuclear program. Here I have the geometrical theory of radiating surfaces with discussion of light tubes. Okay? Now this has to do with the inverse square law and Lambert's cosine law. But what's most important about all this is that, I don't know if you can see it, yes, since these two laws are deduced for sources of infinitesimal dimensions, errors of considerable magnitude may result in applying them to extended sources. Okay, extended sources. Does not apply. So basically what they're trying to do is use the law for light and use it as a law for a gamma ray that comes out during that daughter decay into stability that travels in a straight line from a point and into the detector tube, seeing the ionizing event. Okay? So, let's see if we can make this two-dimensional world make sense in our three-dimensional world. I want to show you a diagram. Now, all these pages here is the math they're explaining of how they can apply the inverse square law and the cosine law to extended sources of radiation. And it has to do with finding the points of the aggregate. So various points. Okay? So I want you to just picture a person watching a TV. This is the person, that's the TV. Okay? Now, how does this formula and this diagram and all this math using constants, because a photon travels at the speed of light, but we have to understand that is only correct in vacuum. In vacuum. In vacuum, it travels 299,792,458 meters per second. But not in vacuum. Does it? What about refraction? What about other things? Air attenuation. Okay? How does this equation equate to life? Is what I want to know. So if there's anybody out there that can make all this make sense, where it equates to not a light bulb, not a candle, not a source of light, but actually Fukushima. I want someone to tell me, since our Geiger-Müller tubes, the tube that's inside of here, You can kind of see it shine a little bit in there. But there's a glass tube in there. Okay? How does that equate with a gamma photon that could be or could not be, most importantly, could or could not be, since it's not in vacuum, could or could not be, where is it at here? I'm going to find it. There it is. Okay. If the rectilinear propagation of light is assumed. If the rectilinear propagation of light is assumed. Okay? And the only way we can assume that is in space. We cannot do that here. On the surface of this planet, not in vacuum, and with a water cycle. With a water cycle where these water-soluble transuranics and radionuclides are no longer fixed to this plane. They are moving about you 365 degrees all around you. This is a slice of space, not 365 degrees of space. With the gamma traveling, upwards of 10 feet. So how does these equations equate to allowing the inverse square law and cosine law to actually apply to extended sources of radiation? I challenge anybody. I've been studying this for a long time. I've read this section over and over and over. I've done the math. I've done the formulas. I understand it now. Do you? Tell me what you think, guys. All right, thanks for watching. Bye.